Hello everyone, welcome back to Deterministic Optimization. We'll continue our discussion on handling nonlinearity in linear optimization modeling. So the learning objective for this lesson is to learn how to reformulate the convex piecewise linear function that we introduced in the previous lecture by linear programming problem. And then we'll look at an application in statistics or data analysis called robust regression model that involves convex piecewise linear function, and we'll reformulate this robust regression model as a linear program. Okay, so we introduced convex piecewise linear function. Remember, those function, convex piecewise linear function fx can be written as a max of linear pieces. Okay. Each piece is a linear function of x. So what about we want to minimize that? So we want to minimize fx, which is given by this complicated form here, which is nonlinear with linear pieces. We want to minimize over x, and x may be contained in a certain feasible region, denoted as a big X, which is a set of feasible region for x. So this is a minimization problem for convex piecewise linear function, and it's a nonlinear optimization problem. The question is, can we reformulate this as a linear program? And the answer is yes, we actually can reformulate this nonlinear optimization problem as a linear program. And here is a general principle of how to do this. The way to do this is I'm going to introduce a new variable, which is not here. A new variable, I call it z. And I use z essentially to replace the entire objective function here. And the way I replace it is I say z is actually greater than or equal to fx. Okay, fx is this objective function. And then I put this in a constraint and minimize z. So if we look at this problem, because we're minimizing z and z is greater than or equal to fx, so then in the end, z will be equal to fx because we're minimizing z. So I'll push z as much as possible down so that it actually equals fx. So in the end, this new problem actually is equivalent to minimize fx itself. So this is an equivalent reformulation of minimize f of x. And this is a general way. It doesn't matter what fx is. You can always reformulate any minimization of a complicated objective function by introducing a new variable and put in the new constraint fx less than or equal to z in the constraint. But once we do this, the advantage is now I can plug in what fx here. Fx is the maximum of linear pieces. So this whole thing, the max of this m linear functions should be less than or equal to z. And we're minimizing z. And then I can reformulate this constraint here, this complicated constraint, because z is greater than the max of m pieces. Therefore, z has to be greater than each piece individually, right? So that is equivalent. So if z is greater than ai transpose x plus bi for all i's from 1 to m, then z should be greater than the max of these m pieces. So this orange problem and the green problem, they're equivalent. But look, this orange problem now is a linear program. So that's how we reformulate this minimization problem of a convex piecewise linear function as actually a linear program. Only trick we need to do is introduce a variable z and bring the objective to the constraint as fx less than or equal to z. Because each piece here is linear function, in the end we'll have linear program. So this is all the trick that we need to reformulate any minimization of convex piecewise linear function as a linear program. So let's look at some examples. For example, absolute value function, absolute x should be less than or equal to z, can be reformulated as follows. Because the absolute value function, in fact, is a piecewise linear function as max between x and negative x. So that should be less than or equal to z. Therefore, x is less than or equal to z, and negative x is less than or equal to z. Or equivalently, you can write it as x less than or equal to z, x is greater than or equal to negative z, because negative x less than or equal to z is the same as x greater than or equal to negative z. So that is a linear program. We have two linear constraints. Okay, a little bit more complicated. If we have a linear function inside absolute value, then this whole thing less than or equal to z again is the inside, which is a linear function less than or equal to z or greater than or equal to negative z. But again, this is a set of linear constraints. So let's look at our Georgia concrete problem. We have this problem: minimize total transportation cost involving absolute value of linear functions. And each of this term here is a convex piecewise linear function. And we can use the technique that we just introduced to reformulate this. We introduce a new variable for each absolute value term or each convex piecewise linear function term. For example, z1 for this term and z2 for this term, and so on. And then we bring this z1 should be greater than or equal to the absolute value of x1 minus x2 in the constraint, but that is the same as x1 minus x2 is less than or equal to z1, greater than or equal to negative z1. We do this for each term. Y1 minus y2 should be less than or equal to z2, greater than or equal to negative z2, and so on. So everything, every new constraint here is linear plus all the other existing constraints. So overall, we reformulate this nonlinear problem into a linear problem. So now let's apply this technique to a machine learning or data analysis problem called linear classification. Imagine you have a set of training data, xi and yi's, where xi is an n-dimensional feature vector, and yi is a label of value either 0 or 1. You can think about each xi represent a vector of, say, lab test data of a patient, patient I. So patient I does some lab test, and the result is a bunch of data, a bunch of numbers. That numbers, say n numbers, that's the dimension of xi. So xi is the vector of the lab test result, and yi is a label that the doctor looks at the result xi and determine if this person has a certain disease. Yes, meaning 1, yi is 1, y0 means this person does not have that disease. So linear classification is the problem that we want to have an automatic machine to do the diagnosis. Given the lab test result x, we feed this into a linear function in this form. It's a linear function. And if this linear function, the result is greater than, say, a threshold 0.5, then we classify that this patient has that disease. Y is 1. Otherwise, if fx is less than 0.5, then we classify the patient does not have the disease, so we label as 0. So this is a linear classification problem. It's called linear because the classifier is a linear function of the feature vector x. The problem is we need to decide or determine the b's. These are the variables we want to determine, and that will give us a linear classifier. So how do we do that? The classifier is constructed by minimizing the total prediction error on training data. So what we mean by that is the prediction error is a measure of the distance between classifier's output, meaning using our linear classification of what is the prediction, versus the true label. So the doctor already labeled a certain amount of data points, and we use that to train our computer to come up with a linear classification. And the computer model should minimize the distance or the error between their prediction and the doctor's prediction. So we see that there is a function related to distance again. And there are many different ways. As I already see, there are at least 2 ways to measure distance. And we'll use the L1 metric again. And when we use L1 metric, the resulting problem will be called robust regression model. So here is the L1 distance. This part, B0 plus the sum, is the linear classifications result, and yi is the doctor's label. So we want to look at the distance between the two for each data point yi over xij. So this should be xij here. So this is the distance for the data point I, and we want to sum over all the data points we have and minimize the total L1 metric distance. So this is the robust regression model. And we see that this is sum of absolute value functions and minimize. Each absolute value function is piecewise linear convex function. So we can just use the trick that we just introduced to introduce a new variable zi for each absolute value term and reformulate. The absolute value term less than or equal to zi is the inside less than or equal to zi and the inside greater than or equal to negative zi. And each constraint is a linear constraint. So for example, this is a set of training data. We have two labels. Blue means 0, red means 1. And doctor already labeled all these points, 100 points here. And we want to build a classifier to separate the blue from the red. And if we solve the robust regression problem, the classifier that results from that is this linear line here. And if you look carefully, you see that it separates most of the blue point from the red point. So that's the result of this robust regression model. Let's summarize. We introduce a general way to reformulate any convex piecewise linear minimization problem as an LP by introducing a new variable, move the objective to the constraint. And we apply this technique to a machine learning problem called robust regression. The focus here is not the formulation of the problem, but how to reformulate the robust regression model as a linear program.